Thank you everybody for showing up. Please pardon my appearance. I don't know why it looks like I'm all of a sudden in a basement. But we're going over the Nitro Whitepaper today with some of the beautiful minds behind the tech stack. We have Daniel G over here to my left on my screen and Lee below myself. And we're also waiting for Rachel as well. Pretty much just some of the wizards over here making the magic happen, behind the tech. So yeah, the main kind of topic here today, obviously, is to go over Nitro. For those who don't know, we just launched we just did the migration from Arbitrum Classic to Arbitrum, a Nitro on Arbitrum 1. So pretty much if you use Arbitrum 1 today, you're literally using Nitro. We're really just going to go over kind of like the white paper and anything extra that Daniel, Lee, or Rachel deems to be relevant. So yeah, in that case, I'll let you guys go ahead and take it away.
Cool. Okay, just kidding.
If you have any questions, by the way, let us know, like in the chat. Just like go ahead and type anything in there, and then we'll try to address it as time goes on. And bam, Rachel's arrived.
Yes, yet. We'll see if I drop out again.
All right, awesome. I think Daniel G just kicked himself out.
Sorry about that. We're having some technical difficulties, but
no worries.
To start off, I think it'd be a good idea to give an explanation of why Nitro in the first place. You know, we had an existing Arbitrum chain. Why Nitro? Well, from a user perspective, as most of y'all know, we had to unfortunately pause the Arbitrum Odyssey because we were seeing such high demand for it, and it was driving up the prices of everything else, because all of that demand our classic system couldn't handle. And that's one of the that's one of the core benefits of Nitro is speed. It's to make it such that we can execute transactions at the same speed as your computer can execute transactions, whereas before we had to virtualize them. So to go into that a bit, Rachel, do you want to explain Mini and
yeah. So y'all can hear me okay, right? Just making sure. Okay, fantastic. So essentially, here's kind of the way I think about it. Originally, in the classic model of Arbitrum, as we call it, we came up with a roll-up protocol that lets you prove the correctness of any arbitrary program written in this special programming language called Mini. So we happen to write a special program in an Ethereum virtual machine that we sometimes call like the AVM. And we essentially wrote this special program that works like an Ethereum virtual machine that you're able to contest using fraud proofs. A lot of details we'll get into a little bit with this paper. But essentially, you were able to prove the correctness of this machine if it was written in that language. Well, that's wonderful. That's very powerful. We were the first to do it. We're very proud to be the first to do it. But like, there's a little more we can get. And that's the ability to prove the correctness of arbitrary programs. That is, not ones just written in this special programming language Mini, but like Rust and Go and C and C++, all these things, right? So what we did is we came up with this new way to prove things that works on WASM. So all of these special, WASM stands for WebAssembly. It comes from a standard that like people are using in browsers and stuff. Well, without going into too much detail, essentially we're able to take any program that can be compiled to WASM, which can include Go, Rust, etc., and we can prove its correctness. Now, there's a very special program that can be compiled into WASM, and that's Go Ethereum. So Go Ethereum is this program that everyone's running to do their like L1 stuff. Now, typically right now, I guess until the merge, it's more mining based. You need 51% of them to be honest, yada yada. But essentially, we've come up with a way of taking the Go Ethereum program and proving its correctness as our layer 2 operating system, our thing that takes transactions and updates the state. It does what's called the state transition function, as you're going to see when we get into this paper. So that's kind of at a high level what to think about. We used to be able to prove anything in Mini. Now we can prove the best program ever, Go Ethereum, right? And we can do it quickly, running at native speeds. It's extremely fast. It's secure. It's something we're very, very proud of and think is really awesome. And we hope that by going over this whitepaper with you, you'll see too why that it's really cool. So yeah, that's how I would describe why Nitro.
Yeah, and I think I would just say what you were just describing there. So this like new proving system and this new way of using it as a virtual machine or within the virtual machine is sort of the core of Nitro, and that's usually like what we're talking about when we talk about Nitro. The white paper also covers a number of like peripheral related things that have also ways that the system has sort of improved and evolved over the years, like let's say since the initial testnet, which the OGs remember was on Robston, I think. It was early 2020. Pretty sure that's right. Yeah, the white paper covers all of that too. So we'll see what we can get to in an hour. I don't know, but maybe we'll touch on some of the other related things like the sequencer, cross-chain messaging, and things of that nature. But yeah, it's exciting to have the white paper out because this is sort of one place that really does describe the full system. So if you can read through all of that and understand all of it, I would say you know how Arbitrum works and how Nitro works. Cool. So with that, should we get into things?
Let's do it. I can share the white paper. You can, I think. Would you like me to do it?
Go for it. Take the honors.
Okay, is this working?
It's an interesting question in the chat. We'll come back to that question, Donna, in a second. Yes, it's working for me anyway.
Perfect.
Sweet.
Great. All right. So
initial sections here, yeah, we have kind of overview sections. These are all things we can sort of get to later. Maybe it makes sense to just, yeah.
Should we skip to the first?
Skip to the first like bullet point, yeah.
Okay.
Which yeah is probably the sequencer. So I can get us started here. So this is again one of these things that's sort of tangentially not directly related to the proving system or to the VM, but still an important part of the stack, which is the sequencer. So one interesting thing about this, and this is true of a number of things in here, again, in the initial version of Arbitrum, there was no sequencer. And this was something that we added over time for various reasons. But to talk about what the sequencer is, essentially, this answers the question of how transactions get ordered, right? So Arbitrum itself, an Arbitrum chain, is a blockchain. We have to get the inputs from somewhere. Those inputs, we have to do some execution, and then the results kind of get finalized. So the sequencer is just all about how those inputs arrive. I guess for starters is the thing to understand. And one nice thing about the design, and a lot of this has to do with the protocol, but also just the way the code base is architectured, is you can kind of just sort of separate the sequencing stuff from everything else. Most of the system kind of doesn't have to know or care where transactions came from. It's just sort of they arrive at some point in the inbox, and then we do the core Arbitrum rollup Nitro thing. If my memory serves me correctly, Lee, I think you actually did a lot of work when you around when you initially joined into actually implementing all the sequencer stuff.
Yeah. Yeah. So we went through a few different models of the sequencer and settled on the one we currently did, where there's basically two inboxes, and this is about how Arbitrum Classic worked too. There are some improvements to the sequencer, which we'll get into later with compression, but there's basically two inboxes. There's the delayed inbox, and then there's the sequencer inbox. And the sequencer inbox is how most transactions get included. You send your transaction to the sequencer, and the sequencer includes it on L1 in exchange for a small fee to cover the costs of posting it to L1. And there's also the delayed inbox, though, if you'd prefer to go directly through L1. So the sequencer gets to decide when delayed messages run, but it has a requirement that delayed messages can be delayed for no more than 24 hours after they were posted. So this is why the sequencer can't censor transactions. It's because if you send in a transaction through the delayed inbox, Nitro, or the properties of the system are, if it's not included within 24 hours, you yourself can step in and force it to be included, or anyone can. And that will force the chain to make progress.
Yeah, and the way I kind of think about in terms of the motivation of having this entity like the sequencer is what it lets you do. The sequencer can give these kind of instant receipts, what we sometimes call like soft confirmations. And this was again like back in the day before there was a sequencer. Instead of having an entity that has this role of sequencing transactions, you could just say you post them on chain, and that's how they're sequenced. So you're kind of just using L1 for sequencing or for ordering. You could think of it as you're sort of just like reverting to the miners themselves and to be stakers for ordering. And basically one bit of feedback we kept getting from projects was like, L2s should be faster, right? And in this case, it's actually, if anything, a little bit slower because you have to like wait for a batch to be posted before you get a receipt. Yeah, so this is kind of the middle ground. I think most other L2s have done something at least vaguely similar, where you you sort of have, like Lee was saying, these two inboxes. You grant this one special party or this one entity the affordance to post directly on the core inbox, but then there's this sort of alternative path to get there. And yeah, the key thing with the alternative path is you can get truly any transaction in without interacting with the sequencer at all, in principle. In the happy case, the sequencer will always sort of do the work, the final step of posting your transaction in the inbox. So you preserve censorship resistance. And the 24-hour thing, which is currently in the white paper, which is a funny thing because we'll probably have to update that, but oh well, it's a PDF, it's fine. It is currently 24 hours, and that's basically the reason that's as long as it is it's sort of just like to plan for the unplannable things, which is to say, if for some reason things go wrong and the sequencer has some downtime, which hopefully doesn't happen often, hopefully it doesn't happen again, but it has happened before, just for sort of like infrastructural reasons. We want to sort of give ourselves enough time to get the sequencer back up before someone can start force including messages. So 24 hours is a pretty conservative window. And I think there is talk about, in the not so distant future, lowering that. But basically, the force include thing is necessary for censorship resistance, but it's also, in the happy case, you want to avoid it being used. Because if someone force includes a transaction that the sequencer doesn't include, it kind of surprises the sequencer in a way. So now you get something like a layer 2 reorg, or the sequencer's receipts are sort of perhaps invalidated, or at least slightly inaccurate. So we give ourselves enough time to make sure the sequencer can include things, but we preserve full censorship resistance without the sequencer. Anything else to add here? It's like not the most fun topic, but it's important.
Yeah, I don't think so. It might not be fun on a technical level, but it certainly is fun to use Arbitrum and see your transaction go through instantly. I had to go back to using Bitcoin a while ago, and I'd forgotten how slow Bitcoin is compared to even Ethereum or especially Arbitrum. I was just sitting there waiting and waiting, and then the fee went up, and my transaction got pushed back even further in the queue. So Ethereum already improves on that with EIP 1559, which makes it a lot more certain when your transaction's going to get in. And then Arbitrum with the sequencer makes it pretty much instant when your transaction gets included, because the sequencer is able to essentially very quickly deliver you a promise about when your transaction will be posted to L1.
Yes, so you're right. It is the most fun thing from a UX perspective. And it is ultimately why, again, we were sort of reluctant at first to even introduce it, but I'm very glad we did, because the UX, even versus just using Ethereum layer 1 of just those instant receipts, feels very good. And the important, I guess here's another thing to just say here while we're on the topic is like, the sequencer currently is centralized and we run it, and we have a path forward to distribute it or decentralize it, which we can talk a bit about if we want. But the more important thing that I like to just say whenever I get a chance to is that even with a totally centralized sequencer, the power that it has, again, is very constrained. It literally has power over ordering your transactions, right? So it could reorder them to extract MEV if it wanted to. It could make a promise to include your transaction and then not, which would be an unpleasant surprise. But that's kind of it. Once things are posted on chain, the sequencer is out of the picture. So we do want to decentralize the sequencer, and we will, and that's something that we need. But it's not like the most important. It's actually not the most important part of the system to decentralize. And I think decentralizing the sequencer has kind of like become this meme that people like to bring up. But it's good, but not the most vital thing. And also, I would just add, even now with a centralized sequencer, if you don't want to rely on it for anything, you can just wait. So instead of taking the instant receipt as a receipt or as a confirmation of your transaction, you can just wait usually a few minutes till the sequencer posts it on chain. And we have client-side tooling in our Arbitrum SDK that tries to make that as easy as possible. So, so yeah, decentralizing the sequencer good, but even centralized sequencer, you could still kind of call the system trustless on some level. Yeah.
Yeah, maybe now would be a good time to go through some of the questions we've gotten since we started.
Yes, absolutely.
Yes. So one of the first questions was, in the same way you make ZK apps instead of ZK rollups, does it make sense to make optimistic apps? Well, frankly, if I had to guess on why people are making ZK apps, it's because it's because they can't make ZK rollups yet. Like I think optimistic rollups are our strength, and the fact that we actually have one live with fraud proofs that work is an amazing feat of engineering. And I think it represents why we chose optimistic rollups. Now, in theory, yes, you could make an optimistic app. We'd previously talked about how you used to only be able to prove mini programs with Arbitrum Classic, but with Arbitrum Nitro, we've expanded that to any Wasm program. And what that means is that anything that compiles to Wasm, which is pretty much anything, that includes C, Go, and Rust, you could, in theory, compile to Wasm and then prove on layer 1. But the reason why we've built an optimistic rollup and not optimistic apps is because, frankly, that's what we think people want. People love the experience of using a network the same way they use Ethereum, having all of the apps they're used to be deployable there. And I think also the fragmentation that comes with individual apps being their own L2s can be avoided by having a single optimistic rollup instead of optimistic apps. So our technology allows for optimistic apps, but currently we think the best approach is just to make an optimistic rollup, which can then host all of those distributed apps on it.
Yeah, I would say the real advantage of an optimistic app, or it's, you could think of it as an app-specific optimistic rollup chain. I think that's basically the same thing. You could, that app in itself maybe could be more performant than something that's using a general purpose EVM. That's really the only reason to do it, I guess. But yeah, I mean, in practice, we haven't really seen these things manifest. I remember back in the day, IDEX was planning on doing something like this, but I don't know if it ever eventuated. But it's an interesting idea, and yeah, I mean, it's cool. But again, like Lee said, there's clearly, even in a world where we do get some of these optimistic app-specific things, there's clearly demand for optimistic general-purpose EVM chains. So that's sort of the niche we're filling, and yeah, so far that seems to be the primary demand. But yeah, I think experiments with app-specific things are definitely cool as well. Yeah. There was another question that caught my eye that I now can't find. Something to do with the sequence.
Was it the one about forcing a transaction after 24 hours, or was it something else?
Oh, I see that one. Yeah, so basically the flow, there's one from Donna here about, yeah, the flow is essentially you would submit your transaction at a given time, and then if the sequencer is behaving, it can include it onto the main chain at any point. But if it doesn't for 24 hours, then you can actually include it into the Arbitrum chain. So so in this case, it would get included after the 24-hour period, right? So currently, if the sequencer were to do that, the sequencer stops behaving, it's definitely inconvenient. But sort of the key guarantee here is you can literally force include any transaction. And in the worst case scenario where the sequencer is just like being chaotic or just not responding at all, you can force a withdrawal in. So you have a guarantee that the sequencer can't disrupt the system and sort of rug the chain. There's versions here that we've kind of discussed. There's things like, I mean, again, we can decrease that period. That's really just there to be again, to sort of plan for the unexpected. There's things you can do depending on what exactly your threat model is. Maybe this is getting a little too weird and off topic, but if your threat model if you're not worried about the sequencer being malicious, but you're worried in practice about it having some downtime, There's things you can do, like have fallback nodes that effectively behave like the temporary sequencer. And here you're just sort of trusting that when the sequencer boots back up, it doesn't do anything weird. And then you can sort of effectively treat your transaction as finalized and part of the chain before the 24-hour period. But yeah, maybe I'll just leave it at that. To answer your question, yes, it gets included after 24 hours in the absolute worst case currently.
Yeah, but our sequencer doesn't wait 24 hours to include delayed messages. This is mainly here so we can't censor essentially, and that in case even if Arbitrum disappeared, you could still get your transaction included via this mechanism.
Correct. The sequencer waits a few minutes, and that's just for protection against L1 reorgs, basically. So yeah.
Exactly. As for why we don't instantly force include, that would basically be a system without a sequencer. And the disadvantage of that is that you'd have to wait for L1 to settle before you get your L2 state. And we want to be even faster than L1. And certainly seems like people enjoy that experience, and we do too.
Yes, and that was
about.
Sorry, go ahead. Yeah.
Oh, sorry, not to change topics, but I did see a question about full homomorphic encryption. Currently, our approach to that is if you want it on Arbitrum, go deploy it. We're fully EVM compatible, so you can write your own smart contracts and go do whatever you want. That's one of the best things about Arbitrum is it's the same experience as Ethereum in terms of writing smart contracts, deploying them. It's just a lot cheaper.
Yeah. Yeah, I was just going to add, just maybe for Donna, a lot of good questions from Donna. One way to think about it is if we allowed like forced inclusion instantly or after like 10 seconds or something like that, but still tried to do these instant receipts, then there's constantly this risk of those instant receipts being invalidated. You basically, if the sequencer is giving these instant or near instant receipts, you want to ensure that the sequencer has a chance to post them on chain in a batch before a forced inclusion happens. So that's why, yeah, even as we get lower than this 24-hour period, we still want some buffer there to preserve that guarantee or that at least hopeful, I don't know, assumption, whatever. In other words, like we're just hoping that the sequencer has enough time to post a batch before something in the slow inbox gets force included. Yeah, that's the idea.
All right, let's move on to future topics then. It's fun answering questions, but I don't want to not be able to get through the things. So
yeah, in fact, one of the questions a good segue, which is advantages of Arbitrum Nitro over old Arbitrum, and maybe just as we move forward, that will become clear. Yeah,
sounds good.
Cool.
So do we want to go over how transactions make their way into the blocks essentially, or?
Yeah, we can talk a bit about this, and then we can get to like the real like ArbOS improving and stuff. But basically,
sure.
Yeah, I guess just like this step of things. So now we're post sequencer. The sequencer's posted the inputs on chain, and now the claim that we can make here, like literally the claim we're making now as people, is that at this point we have enough data on chain to determine what the state of the Arbitrum chain is. And this is what we mean in this paper by deterministic execution. So we have, it's entirely deterministic. The results of execution are entirely determined by the inputs, and the inputs are all available because that's guaranteed by Ethereum security itself. So the moment things end up in the inbox, usually from the sequencer again, but however they end up in the inbox, you can sort of consider them as finalized with respect to layer one, even before anything else happens. I think that's a weird way of putting it, but yeah. Is there anything else anyone wants to add there? And that's because the state transition function is deterministic, and really it's because of what we'll talk about next, which is how we actually ensure that the proper state root gets settled.
Yeah. Let's see, do we want to get into ArbOS then?
Yeah, let's do it.
Yeah. So ArbOS is essentially that program that we're proving over. It's Geth at the core. So we say in the sense of like we call into Geth and we use its Ethereum virtual machine to update the state in the database that it has associated with it. And that's kind of like, that's the name for that program. Now, originally, this was that piece that was written in that other language, Mini, and we essentially rewrote it from scratch to instead be in Go and call into Geth as if it was like a library. You could see it that way, and yeah, there's some technical details you could see on this page about like how exactly we represent state and stuff. You might find this interesting if you're looking in the explorers. There's some like special addresses that start with the letter prefix for ARBOS. But essentially, like we actually store the state of the state manager in a special contract. So there's like this special address that has no known private key, of course, because it's like it's a human readable one, and like essentially we just have this like structure whereby if we need to manage accounts or contracts or do these special things we call precompiles that let you have access to certain unnatural behaviors that you want to have but you can't really get out of Solidity. When you do these various things that we'll go into, basically it maintains the state, updates it, and stores it in the very state trie that all of the accounts and contracts are in. And this is very important because it means that ARBOS itself changes in response to transactions from L1. So the state of the manager changes with transactions, which therefore means that it's still a state it's still a state function over the L1 inbox. So you can be confident that like everything's deterministic and all of that. And if you actually look at the code of it, you can go on a little exploration and see how like it's essentially this big system where when the transaction comes in, it might service various requests for it. I sometimes think of it as like a hypervisor. You call out to go do something. It's not exactly that, of course, but yeah, I guess that's what I'd say as a high level overview for it.
Yeah, I have a question. First time caller,
Sure.
Big fan. Is it fair to say, is it accurate to say that ARBOS is the state transition function, or is that like kind of off? And
I think that's a fair way to say it. It's like I mean, the real meat of the state transition function is calling into Geth, doing all the gas counting and stuff like that. But there is stuff that happens in the middle of that transition, right? Suppose I call out to a precompile. So for example, there's a special precompile called ARPSys that will let you withdraw ether from the system. There's of course no like way in Solidity to say, hey, withdraw ETH to L1, right? There's no notion of these things. So you need this kind of like virtual contract, we call it precompile, to go do these state functionalities for you. So part of the transition to a transaction that might withdraw something is calling out to ARBOS. And you'll actually see the precompiles are written in Go. They're not actually written in Solidity. So and there's a lot of them. So we have all sorts of various ones for accessing special tables to make things a little more, to make things cheaper if you want to use those features. We've got stuff like withdraws and outbound messages and like various things around gas counting, like if you want to introspect into like what happened but when you started the state transition. But basically we have all these functionalities and those are part of the transition that happens. And then at the very end of the process, ARBOS closes out the state and commits to Geth's internal database the new state trie, which includes anything that you may have changed inside ARBOS itself, because ARBOS is a member of that state trie. So I think it is fair to say ARBOS is the state transition function, though really when we say that, we mean it's like the specific, the state transition function is like the specific set of things that you might access as a transaction versus the other code that you might use if you're like just a node doing things and, making ETH calls and all of that. So I think it's a fair way to divide it up.
Cool. And yeah, one of the really nice things about this new architecture, if you're just trying to sort of understand it or even looking at the code base, is in the old version, given, in the old Arbitrum classic stack, you effectively have a blockchain system implemented from the bottom up. So down from a custom virtual machine, the AVM, and then ARBOS, which kind of included all this other stuff that sort of had to be implemented again, largely in Mini. Whereas now you sort of have Geth itself, does a lot of the heavy lifting, and now the ARBOS stuff that Rachel was talking about, the implementation, is mostly, if not entirely, just sort of all of the new stuff or differences you have to add that are sort of L2 specific, which is like very nice because it just sort of feels right that we have an EVM compatible L2. We can use Geth, we can use the EVM, and then we just add this new code that does L2 stuff. stuff which we'll get into at some point. Maybe not in this stream, but yeah, things like again the stuff Rachel talked about, cross-chain messaging, special affordances with gas, the new precompiles, so that's just nice, even if for no other reason. That's one of the really nice things about Nitro, is it's just like a lot less new code to reason about, which is just good for everyone. Yeah.
It's also very cleanly separable and like makes it easy to audit and think through and also optimize, right? So we don't have to like go into the internals of the Ethereum virtual machine to do certain things. Instead, like if there's some special precompile that needs to happen, it can be written in Go, and then that stuff happened there. And because this all compiles down into Wasm, right? Even though various portions of it are written in Go, we've got our contracts in Solidity, we've got our like, we have some Rust and some, I think also, let's see here. Oh yeah, and then there is some C because we do compression through a C library. All this stuff gets turned into one Wasm that then we are able to like prove over and stuff. And you get to see some of the generality in the design of ArboS and the infrastructure around it.
Yeah. On that note, do you want to maybe just, I feel like you're on a good roll here. Do you want to, if we go ahead to like the Wasm stuff, I think section 4 or Wasm.
Sure, let's do
sort
it.
of a natural transition. Yeah, we can hop back to the cross-chain messaging stuff.
All right.
But since it came up, yeah.
Yeah, so let's see, let's get into, okay, so compiling for execution versus proving.
Yeah.
So historically in Arbitrum Classic, as we mentioned, you would write everything in Mini, and then it would compile down to the AVM. And that same AVM binary would be used both if you were a normal node executing the chain, executing transactions, or if you were a validator trying to dispute an assertion or make an assertion or any of that. And this was really nice in terms of proving. It made a lot of sense because the thing you're proving is the same exact binary as the thing you're executing. But one of the issues is whenever you have a layer of virtualization like that, it's slow. And especially when we were having to build up all of these optimizations from the ground up, instead of taking advantages of like all of the excellent optimizations and the various existing compilers for C and Go and Rust, we were having to build our own compiler optimizations. So with Arbitrum Nitro, what we're able to do is natively execute a Nitro node, which means that you don't actually invoke Wasm if you're running a normal Nitro node. When you're processing transactions and executing blocks, it's all just normal Go execution. You only invoke Wasm when you get into proving a block. Because, and how we've done this is we've made sure that the Wasm output of a block is the same thing as the native execution output of a block. So what that means is we can normally execute with native execution and then prove with WebAssembly when we need to. And that means that that a normal node can run at native speed, which is as fast as you can run. It means that the Nitro Wasm architecture is fundamentally as fast as you can get because Wasm isn't even needed for normal execution. You can execute as fast as Go can, and that's one of the big innovations of Arbitrum Nitro. Now, in order to prove WebAssembly, WebAssembly is a bit of a complex assembly, I would say. There are some components of it, for instance, that involve operations which may take a variable amount of time to complete. And one of our requirements for proving execution is that instructions are very simple and only do a limited amount of work in one instruction. Now, with the Arbitrum virtual machine, we were able to design it from the ground up to ensure this. But for WebAssembly, what we've had to do is compile WebAssembly down to a simpler format, where the simpler format will ensure that anything done in the one-step proof, we have a guarantee that it can fit within a single L1 Ethereum transaction. And we call this format the WebAssembly virtual machine, or WAVM, kind of piggybacking off of the Arbitrum virtual machine, AVM. This does a number of things to simplify the WebAssembly format. For instance, it gets rid of the concept of blocks, which were a WebAssembly format, or sorry, a WebAssembly kind of almost notation for where jumps went, and it replaces them with direct jumps. And it also gets rid of floating points, because floating points are somewhat non-deterministic in WebAssembly. You can have a calculation that returns two different things on two different computers, and obviously we can't have that for Arbitrum when you have two Arbitrum nodes that need to both output the same thing. So instead, we've replaced floating points with a existing software implemented floating point library. And these simplifications are what allow us to prove WebAssembly on chain. Getting into some other details here, one question is, how do you manage state, right? Clearly, we can't post all of Arbitrum state to layer 1. That would be impractical. Arbitrum has a lot of state, and that would be extremely expensive to post to layer 1. So instead, what we do is we just post block hashes to L1. And we had a similar mechanism in Arbitrum Classic, where we would just post Arbitrum virtual machine hashes to layer 1. With Arbitrum Nitro, though, we're using the existing block hash format. And one benefit of this is that you can do, for instance, any proving against block hashes or cross-chain messaging type things that you were previously doing with layer 1 Ethereum. You can now use those same techniques for Arbitrum Nitro. And how we actually get state out of a block hash is we use this read preimage instruction. Now, normally, you can't find which input made a hash. This is thought to be computationally infeasible, basically. And what that means is that under normal circumstances, if I give you a hash, you can't tell me what input I used to create that hash. But what the read preimage does is it assumes that everyone already knows the inputs to the hash. And why it assumes that is because everyone was already executing previous blocks and building state, and they should already have these blocks, for instance, saved in their database. So under normal circumstances, I couldn't just figure out what contents a block hash has, right? If you hand me some random block hash, I wouldn't really know what to do with it. But if I had a local node, or I just went to Etherscan and I put in that block hash, I would find out all of the details of that block. And that's the same theory as the read preimage instruction. The theory is, since the nodes already know what's in a given block hash, we can resolve that at runtime, and that's how essentially the WebAssembly virtual machine is able to. It doesn't really have a database as much as it has a fixed storage slot for a block hash, and it's able to look inside the block hash because nodes already know what's in that block hash.
Mm-hmm. Right. We can't reverse hash functions, in other words. But it sounds like despite the name read preimage, not yet. Yeah, so that's cool. And the use of, the way I think about it, let me know, is that the use of just having these intermediate representations of blocks and block hashes is sort of why we can separate execution from proving. Maybe we'll get to that when it comes to proving. In other words, we have a way of representing the state that isn't at the WASM level. But either way you execute, whether it's WASM or running GoCove natively, you'll get the same state.
Yeah, that's exactly correct. And that's why, for instance, in the old system I mentioned, we committed to an Arbitrum virtual machine hash instead of a block hash. What that meant is, even if you knew what the new block hash was, you couldn't, for instance, make an assertion about the block hash on layer 1 because you needed the full Arbitrum virtual machine. That's why in Arbitrum Nitro, instead of committing to a WebAssembly machine hash, we commit to just a block hash. And you only involve the WebAssembly machine when you get into disputes about a particular block. And what that means is that if you're running a node, you could make an assertion about a given block hash without having executed it in WebAssembly yet. Now, this isn't advisable. We normally do block validation, which involves running it through WebAssembly in parallel. But The change in format means that execution is detached from proving because they both output the same block hashes, and block hashes are what's used to assert a given state on layer 1.
Right. We do block validation in WASM for active validators currently, right? So for people who are have staked claim and we're posting assertions, and that's sort of a level of insurance essentially, where you can just guarantee that your native execution and your WASM execution converge. But if you're just running an Arbitrum node and not making assertions and stuff, we just do native execution, right? I think
we do native execution, though we have actually just earlier this week introduced a just-in-time accelerated, a so-called JIT accelerated block validator, where we actually take advantage of like the optimizations LLVM might do to create to transform the WASM, that the replay binary, the thing we're actually replaying and stuff when proving, into x86 or whatever your platform has, and then runs that. And we found that like we're actually able to use this to validate blocks at like 8 million gas a second, which is really, really good. And it means that like a block can be done in like, order of tens of milliseconds. And it means then that even if you're not like, making assertions and using arbitrator to like, actually dispute a resolution or something, you're still able to like see the integrity of the system and see that things are checking out and making sense. And so we imagine that like people will generally want to use that. But if you want like the full, arbitrator driven one, you can use that as well. So, there's and it's also an embarrassingly parallel process. So like the more parallelism you have, the more you can validate per second. So with our recent improvements, we've made it really fast such that you generally don't need tons of it. So yeah, cool. And also, by the way, that kind of goes into like why we chose Wasm. There's a lot of reasons into it, but I think one of them is just it has some incredible tooling and very robust, and a very robust ecosystem that spans all sorts of projects and languages. I mean, it is a WebAssembly standard, so that means like, it's got like the backing of all these like very vested parties. And like what you'll see there, and for example, in the JIT accelerated one, that like we got to take advantage of really great tools like Wasmer, which are harder to find on like alternative things that you might want to prove. And also there's, of course, just naturally nice things about Wasm, like it's extremely sandboxed, right? This is designed for a browser. You don't want people to be able to do things. And, browser's like one of the most adversarial environments there is. So, having something that was designed for that is just very elegant and nicely fits into the Arbitrum rollup protocol. So Wasm was a great choice, and although we do the transposition into WAVM for the arbitrator specific stuff, that Wasm is still very valuable on its own, and we do things with it. So yeah, that's a little bit of insight into that kind of thing.
Word. Also, just lots of things can compile to Wasm, so that could become useful for all sorts of reasons. Okay, should we talk about the sort of fraud-proof game, interactive proofs, and so on that might be a next logical step? So yeah, I can sort of get us started here, I guess. So this is a very similar principle to what was going on in the pre-Nitro classic protocol. The idea, essentially, on a very high level, being we have these state roots. We have a pre-state and a post-state, and if two parties disagree about the post-state, they disagree about the state transition, they're going to play this interactive game where they sort of narrow down their disagreement into a single computational step, like a single opcode, and kind of execute that. With Nitro, so with the old version, again, this was all like a custom virtual machine, the AVM. That's what we were both executing and bisecting over, doing this game over. Now with Nitro, the virtual machine itself is Wasm, or Wasm. And the bisection, as maybe we were sort of getting to earlier, sort of dancing around, but this bisection process now kind of has these two phases, which is pretty cool. So instead of just sort of committing to a sequence of operations and bisecting those down to one, we commit to effectively a sequence of blocks. We start by bisecting down to a single block. Once we get that down, then we start bisecting over the state transition within that block, all of its WAVM steps. And this is neat for a few reasons. Basically, but the main thing that it gets us, I guess, is what we were alluding to earlier, which is you don't actually have to sort of execute things at the WASM level. I'm just going to say WASM. It's too hard to say WASM. You don't have to execute things at the WASM level, unless you technically don't have to until it's absolutely necessary, which is to say when you're in the middle of a fraud-proof game. Otherwise, you can just sort of execute and think in terms of blocks. So you don't kind of open up the block into its WASM steps until it's absolutely necessary. So we get this like very optimistic execution, which is cool. And that's, I think, a lot of the performance. I think a lot of the performance included improvements that we got with Nitro are sort of downstream from that, or at least a big one. I kind of brushed over the details of the fraud-proof game, but if you're not familiar, yeah, we can talk a bit more about what that looks like if we want. But that's like section 6.1 here. Yeah.
I don't think we need to talk too much about it.
Maybe we don't, yeah.
The general idea. What?
Yeah.
Just the general idea is, you make an assertion. If someone else disagrees with you, which should be rare because, again, we're an optimistic protocol and nobody wants to burn their stake. If someone disagrees with you, then you first narrow it down to a specific block by bisecting, which means you keep narrowing down which range the block is in until you find a specific block that you disagree on. Then, as Daniel mentioned, we unwrap that into a WebAssembly machine execution. You narrow down which range the WebAssembly machine instruction that you disagree on is in until you find a particular one you disagree on, and then the one-step proof executes that one instruction on chain to resolve who is correct.
Mm-hmm. Yeah, and what's nice about this design, this was true in Classic too, with this design, the sort of contracts don't have to sort of, on the solidity level or on the contract level, on the application level, I guess, you don't have to sort of worry about recreating an entire virtual machine. You just need to literally be able to do this dispute bisection process and be able to execute all of the individual steps, it's just nice because now, a lot of the complexity of the system, is in the node itself. But the proving part is sort of, in some sense, surprisingly easy to reason about. You just need,
And if you're interested in the specific details, or white paper goes into a lot of detail here on the bisection over blocks and the bisection over instructions.
Yes. And the stuff that we carried over from Classic is, as Lee said, it requires some stake to make any sort of assertion. And you have this, given that there's deterministic execution, if you make an invalid assertion, it's sort of guaranteed that any honest party will win the challenge against you. So you're not really achieving much other than losing your stake by making an invalid assertion.
So
cool.
Daniel, we could go more over the cross-chain messaging or outbox withdrawals, or we could move on to any trust if you prefer.
Yeah, we can go back to the cross-chain stuff. Were there any questions we missed? I haven't really been looking.
Let me see.
There are a ton of questions, I think, but I'm not sure how. I'm not sure if they relate very specifically to what we're talking about at this point. Then again, I don't speak code, so.
Someone asked about Oh,
good.
Okay, sure. So someone asked about the flexibility of precompiles. It is generally the case that adding them is very trivial. One of the issues with a lot of ZK technology that you're comparing to in your question is that it's very inflexible and you have to design new circuits and stuff. But in our system, you just say, okay, we want a new precompile that has some functionality, and you just create it and install it, and then when you change the WASM module root, as it's called, there's a whole part of the paper on that. You now have access to this new precompile, and it can of course do any arbitrary thing because it's written, it's written in programs or in languages that compile down to WASM, which almost certainly means Go when it comes to precompiles.
Yeah, and I think so exactly. In principle, you could it's just a matter of implementing something in Go. In practice, a lot of we have a number of precompiles. I just linked to them. Most of them are there to facilitate L2 development. So there's things that are just useful for application developers to get a view into what's going on with gas, which we can talk more about, and handling cross-chain messages. It's more, they're more geared towards things like that. But certainly in the future, we could add special features for the sake of it, if we feel like it.
Sorry, didn't mean to cut you off there.
No, that's all. But yeah, no, there was some. I saw something pinned for a second. I'm juggling two screens. Excuse me. But yes, this is a place. I think I will say that supporting things like this, special precompile, special cryptographic curves, things like that, is certainly easier in an optimistic environment than a zk1, because yeah, we just kind of build it. It's implemented in Go. It becomes part of the state machine, so then therefore it becomes something we can prove over. Whereas with validity proofs, you sort of have to solve this new puzzle of how you construct validity proofs over each new thing you introduce. So yeah, we could have some fun with that.
One question I see is about how we divide or we optimize block space. I'm not really familiar with optimism's approach here, which is what's being asked about. But in terms of yeah, unfortunately, I don't think I know enough about optimism to answer this question. Our basic block strategy is we, because of how our proofing works, we have a limit of I think 32 million gaps in a block. So we simply try to put everything we can in a block, while still delivering a good user experience by ending blocks early to get receipts back to users quickly. And then anything that can't fit in that block goes in the next one. There can't infinitely be transactions that don't fit in blocks, because as blocks fill up, the L2 price would go up. And but if we're running under the speed limit, we'll just keep putting transactions in new blocks. And if this question is about compression, which I'm not really sure if it's about compression, I think it's about gas usage, but our compression is also quite good because we can compress whole sequencer batches as one big unit. And I think this is a reason why you see on sites like L2 fees, Arbitrum is consistently one of the cheapest to send ETH or transfer tokens, is because of this new compression technology that we brought with Arbitrum Nitro, where we compress an entire sequencer batch as one unit instead of compressing individual transactions.
Yeah, and someone just mentioned that we have noticed that we have like a BLS related precompile, and actually, so we're doing research and thinking about supporting BLS just like at the user level, at the wallet and transaction level, which hopefully that can happen. But even now, actually, yeah, we do we can and do validate BLS signatures within Nitro, and we're actually using that currently in Arbitrum Nova, which we haven't talked about, but the alternate model, this any trust chain. There's kind of, it's a different model. It's not a roll up. There's a committee, and they have to sort of sign off on batches. And the way we validate their signatures is they're aggregated, and we use BLS. So it's pretty cool because that is happening live and in action.
Yeah, if you're interested in BLS transactions as a user, or as a in user BLS transactions, and you have thoughts on how the transaction format should look or anything, we're currently over at research.arbitrum.io. We have a proposal for how BLS transactions could look, and there's been a lot of discussion on the technical aspects of how we add BLS signatures to transactions, what the format would look like, how wallets would work. And yeah, so if you're interested in BLS signatures, head over there and come chat.
Yeah, and it's basically, the stuff that's required is like coordination on a standard, stuff at the wallet level, and kind of tooling and infrastructure level. But at the Arbitrum level, we're kind of we're effectively ready. So yeah, we're just trying to think of a way to do it. And particularly, we have an eye on supporting a transaction type that leaves the groundwork that in the future Ethereum layer 1 would be able to adopt, because that makes sense. But yeah, take a look at that post if you're interested. Cool. We have a few more minutes left. We haven't covered everything. Yes, go ahead.
No, if we only have a few more minutes, let's continue with the paper. But I'll briefly mention, people were saying, like, could we do alternative VMs and stuff? Yes, the answer is it is possible to prove the correctness of any arbitrary WASM, which then gets transpiled to WAVM. Now, we picked the Ethereum virtual machine because, that's where the rich ecosystem exists. And, you want your smart contracts that work on L1 to work exactly as they do on L2. So yeah, we could have theoretically taken anything. Like we could have taken Solana's VM, say, and like taken its Rust to Wasm or what have you. And theoretically speaking, done proving over that. But we really like Ethereum. There's a wonderful ecosystem there that's now moved into Arbitrum. And I think a major constraining factor to why that kind of thing wouldn't show up in other places is just if your smart contracts don't work. And that's kind of what you lose when you throw in other VMs.
Yep. Oh, that's Preston Van Loon. I assume it's really him. It could be a Sybil, but we have a question from a person I assume is Preston Van Loon. Interesting.
Yeah, so one of the things we are looking at is for a fast sync functionality. And this one, because when we confirm assertions on our layer 1 rollup, we also confirm block hashes. And once you have a confirmed block hash, you could grab the state of that block without worrying about re-executing all of the transactions in the past. And that's one thing we're definitely looking at, especially as Arbitrum 1 continues to add state and transactions and people continue to use it, is that fast syncing from the layer 1 rollup confirmation. Though I should mention that for Arbitrum 1 right now, it's still quite quick to sync because we haven't had that many transactions since the Nitro upgrade. Well, we've had a lot of transactions, but it's only been like a week. So it still doesn't take that long to sync.
Cool. It's probably not quite time to start a new topic, I guess. Maybe we should wrap.
We have like a minute left, unfortunately. Trust is very cool, and as we mentioned, how we solve data, still having to pay for data costs on layer 1 with Arbitrum Nova. You don't have to pay for L1 data costs, but we will cover that maybe on another stream.
We will cover that, and yeah, I guess we covered a lot of like the core Nitro stuff, the core protocol things, but sort of the details of kind of what goes on at the application level, or sort of the actual changes you need to make this thing L2 compatible, like how to handle gas and cross-chain messaging. Maybe that can be a more focused thing for next time.
Yes.
I didn't.
And one final question we should answer though is someone was asking like, do we do internships? Where do I get a job? All of that stuff. We actually are hiring. So we'll post a link into the chat. But essentially, we have a lower page. So all sorts of different disciplines and things we are hiring for. So take a look at that and see if this stuff is interesting to you and you want to be someone who actually writes these kinds of white papers and stuff. You can come join us.
Indeed. So good question, whoever asked that. Cool. All right.
Yep.
We will have to do at least a part 2, maybe a part 3 and 4. There's a lot to talk about, but I think we covered a lot considering.
I think that was great. And yes, just to follow up, I put up a little link in the chat. I'm not sure if it's showing yet, but for our job site, so you can just go ahead and apply there if you're looking to join this amazing team of unicorns. I don't know why I referred to us as unicorns. Apologies. And if you do want to actually contribute to the conversation in terms of like tech related stuff, I'm sure all of you are already in a Discord, so you can always speak in there. But also for sure, we have that research forum that we definitely want to really get kind of going even more so. So feel free to kind of put your thoughts in there. Fellow BLSers.
Read our docs. We have new docs. Always, anything that's unclear or have questions on or feedback on is welcome there too. But the white paper and the docs generally are pretty up to date now, so that's exciting.
Yes. Any questions you guys have just generally though? Our Discord's pretty active, so feel free to jump in there and ask us anything. But yeah, Lee, Rachel, Daniel, appreciate you guys for giving us this deep dive into the Nitro white paper, and we'll look forward to showing the people more pretty soon.
Definitely.
Alrighty. Cheers, y'all.
Adios.
Bye.